This is video 4 for gravity, force, and space. So to start this one, we're going to talk about circular acceleration. Now, as a physicist, we kind of like to define velocities having both magnitude and direction. So the magnitude will be like how fast it's moving in a direction is, well, what direction it's going. So if your velocity changes, then that's an acceleration. However, let's imagine a case where your direction is changing, but not the actual number of meters per second. So you're maintaining a constant speed, but you're going around in a circle. That is still acceleration. And many of the equations we've been talking about will still work. So one of the most important examples of this kind of acceleration is when you go in a circle. So your speed would be v, and that doesn't change. But your direction does. Now you're going in a circle, so that circle has a radius r. So your acceleration then would be equal to your speed squared divided by the radius. And this is very, very important for fighter pilots because when they change their direction rapidly, basically what they're doing is they are going in a large circle. And even though they're maintaining a constant speed, they still have an acceleration. So, just to give you some idea of this. So let's say we have a fighter pilot. So this fighter pilot, she's traveling at 1,000 miles per hour, and she's turning in a circle with a radius of 2 kilometers. We could figure out that acceleration, and what it comes out to be is right around 10g. Now, this means that they weigh 10 times more than they would on Earth. So if you weighed 150 pounds just standing still, you would weigh 1,500 pounds. Now, at this kind of force, you would faint without some sort of pressure suit. The reason for that is because the force is so great, all of your blood goes into your legs, and your heart doesn't have enough strength to push that blood out of your legs and into your brain. That causes you to faint. So the pressure suit applies pressure to your legs, and it helps your heart pump blood up to your brain. Now, this is also this type of acceleration is also important in chemistry. It helps us to separate out particulates in a solution. We call these devices centrifuges, and basically the way they work is that you put a solution into a little vial, it spins it. The more massive particles in the solution need a greater force to keep them close to the center of the circle. Since they don't have that, they go to the outside of the circle. So more massive particles will tend to move towards the outside. We can also use this idea to help us make artificial gravity in space. Many science fiction movies that have like some sort of space station, you'll notice that they're all spinning. They're very large and they're spinning. And basically, people would move around on the inside wall. So this great big craft would have a huge radius. It'd be turning with some sort of velocity, and we know that the acceleration would be v squared divided by r. So all we need to do is we need to make the acceleration equal to g. So what we would need is a small spacecraft that's moving quickly, or a large spacecraft that is moving slowly. Rotating by moving, that is. Another way to create artificial gravity is to simply accelerate. So if I have a rocket, I have a person standing in it, what I would need to do is I would need to make the rocket accelerate. And I would need this acceleration to equal g. So acceleration is equal to a final velocity minus initial velocity with respect to some time. So I would just need to make sure that this condition is satisfied. Unfortunately, it wouldn't take long until you were moving at the speed of light, which is a big problem, so that doesn't quite work out. But all you really need is an acceleration. All right, now, we've discussed a few things before about like escape velocities. So for Earth, the escape velocity is 11 kilometers per second. For Jupiter, Jupiter's much bigger than Earth, it's 61 kilometers per second. And for the Sun, it's 617 kilometers per second. If you wished to leave our solar system, you would need a velocity of 617 kilometers per second. So, if I have something that has an escape velocity of 300,000 kilometers per second, that's the speed of light. That object would be a black hole. And they're given this name because, well, we can't see them, because light does not escape them. So what we do is we observe them through their effects on neighboring objects. So to be a black hole, you either have to have a lot of mass or pack a moderate amount of mass into a small radius. If you were to take the Earth and make its volume about the size of a golf ball, then it would be a black hole. If the Sun were to turn into a black hole, it would have a radius of 2 miles. Now, since the masses don't change, the Earth would orbit that black hole just the same way that it orbited the Sun. All right, the next topic is momentum. This is kind of like an action-reaction thing. If you shoot a powerful rifle, you are applying a force on the rifle. The rifle then will apply a large force back on you. And that's what gives guns their kick. And this kind of goes in with Newton's third law. So if you push on something, it pushes back on you with the same strength of force. Now, the bullet's lighter, so it's accelerated more than the gun. Acceleration equals force divided by mass. So if you think about it, if you're firing a gun, the bullet gets a very large acceleration because it has a force over a very small mass. You, because the gun pushes on you, get a small acceleration because you have that same force, but you have a much bigger mass. And this leads us to conservation of momentum. So the mass of the bullet times the velocity of the bullet must equal the mass of the gun times the velocity of the gun. And that product, mass times velocity, is what we call momentum. So what would happen if the Earth is struck by a very large comet? Well, we would have the mass of the Earth times the velocity of the Earth equaling the mass of the comet times the velocity of the comet. So what I would want to know is, okay, what's the velocity of the Earth? Well, that would be this right here. So a typical comet has a mass of around 10 to the 19th kilograms. They move at right around 30 kilometers per second. So that's 30,000 meters per second. Earth's mass is right around 6 times 10 to the 24th kilograms. So that means that the Earth will have a velocity of 0.05 meters per second after being struck. That comes out to right about 2 inches per second. You would not notice it. Rockets use the same thing. Let's imagine if you took a gun and pointed it straight down and started firing the bullets. And as you fired the bullet, it would exert a force upwards on you. Now, imagine firing bullets as quickly as you can. It sounds silly, but that's actually how rockets work. Instead of firing bullets, they fire out atoms of burnt fuel. And we can use conservation of energy to kind of get a better idea for how this works. So the mass of the rocket times the velocity of the rocket would equal the mass of the fuel times the velocity of the fuel. So once again, we can get the velocity of the rocket with with that equation right there. Now, rockets weigh a lot more than the fuel that they expel. So the velocity of the rocket will be much smaller than the velocity of the fuel. So if I want to improve my rocket, I need to have fuel that has large mass, so like large particles, or as a result of the explosion, I need to make sure that they have a very, very high velocity. Because of this, rockets are extremely inefficient. Roughly, 25, the mass of the fuel itself is about 25 to 50 times larger than the payload of the rocket. And that's a huge problem that we have to overcome if we want to get to outer space more efficiently. Well, that concludes video 4 for this unit.